Good afternoon. I'm Subodh Kulkarni. I'm based in Berkeley, California, and CEO for Rigetti Computing. As Juan mentioned, we are a leader in superconducting quantum computing technology. My talk today is how do we embrace quantum society? We have a very strict time limit here, I understand, and if I don't finish on time, apparently there's an eject switch or something that I'll be thrown out, so I have to be careful. So anyway, what is a quantum society? We envision a quantum society where we harness the power of quantum technologies to do things that are not practically possible today. Specifically in quantum computing, we envision a day when we can solve problems that cannot be dealt with classical computing today. There are many kinds of problems: Ising equation, Bose-Einstein condensate, many complex optimization problems, and so on, that are practically impossible to solve with today's conventional computers. With quantum computers, we get a huge benefit where we can have multiple qubits that entangle, and then we have different multiple states all at the same time. So we are no longer constrained with the classic digital world where we just have zeros and ones and we have to deal with it in sequence. We can do things in extreme parallel mode with multiple states, and that gives us orders of magnitude better capability. We are not talking 10%, 20%. We are talking million or billion times better, faster computers. At the same time, and that doesn't get talked much, they will be consuming a million or billion times less energy. So the power of quantum computing is on both sides, the performance as well as the energy consumption. And energy consumption is getting increasing attention. If you look at AI today and what's going on with NVIDIA and everything, energy is becoming a bigger and bigger factor. We cannot keep building. If you come to San Francisco, where I am, OpenAI keeps building more and more buildings, essentially to house more and more servers, and the energy consumption is going through the roof right now. So quantum computing is needed not only for the higher performance capabilities, but also lower energy consumption. So in the quantum world, we deal with qubits instead of bits. Typically in a classical computer, if you have n bits, your computation power goes linearly by 2 multiplied by n. In quantum computing, when you have n qubits, we go 2 raised to n. So when n is small, it's not a big deal. But when n becomes 50 or 100, 2 multiplied by 100 is 200, 2 raised to 100 is practically infinity. So in about a decade or so, we see what we call fault-tolerant quantum computing. What we mean by that is 100 perfect logical qubits, so 2 raised to 100 computation power. Now, in reality, there will never be a perfect qubit, just like there's never a perfect CMOS transistor. Our state-of-the-art CMOS chips today that we all use in all our advanced devices are typically what we call 99.99% fidelity. That means 0.01% error. The way we overcome that is with error correction, error mitigation, and other techniques. So in the quantum world right now, along with us in the superconducting area, you have companies like IBM and Google. We are all dealing with roughly about 100 qubits, roughly in the 98, 99.99% fidelity range. So we call that noisy intermediate scale quantum computing. NISQ is the word that we use. So today we are all in the NISQ era where we have about 100 qubit, 98, 99%. Our plan is to go to what I said, fault-tolerant quantum computing, roughly about a decade from now, where we will have hundreds of thousands of qubits, maybe a million qubits at 99.9% or so fidelity. And that's where the real power of quantum computing will be harnessed. And that's what we mean by quantum society. We could deal with problems that are impossible to solve. Now, not all these problems are scientific curiosity problems. There are many practical problems that we are dealing with today, such as weather forecasting, drug discovery. Right now, I mean, if you look at what happened during COVID, because of lack of computational power, only about 100 variants of the vaccines were tested. If we had the capability of testing infinite combinations, maybe we could have come up with a better vaccine. And those kinds of problems continue. So we think through the NISQ era, we can keep trying to get closer and closer to fault-tolerant quantum computing and ultimately get there. Different companies have given different estimates about when we think we will reach fault-tolerant quantum computing. We believe we are roughly about a decade or so from now. Now, when we make these predictions, maybe it's 7 or 8 years, maybe it's 12 or 14 years, but we clearly see a path from where we are today to a fault-tolerant quantum computer. So it's no longer a question of if, it's a question of when. You will see different time estimates from different companies, but we are pretty sure fault-tolerant quantum computing is going to happen in roughly a decade or so. So how do we embrace this world where quantum technologies are available to solve problems that we cannot solve today at a significantly lower energy consumption? Let's go, and the answer to that is let's embrace this NISQ era. Clearly, quantum computers are not perfect today. They are very noisy. They cannot be used for any practical applications today. Your state-of-the-art GPUs or CPUs are always going to outperform quantum computers today. But we need to understand and start learning now. You need to walk before you run. And we are in that stage right now with quantum computing. We need to start using these NISQ quantum computers to understand how they are different than classical computers. The whole stack is different. The chip looks very different. The firmware looks very different. More importantly, the algorithms are very different. When you suddenly are no longer constrained by zeros and ones and not on sequential operations, your algorithms look very different. So the entire stack has to change. And you cannot wait till we are ready and say, hey, we have a quantum computer that can take on all these problems. Companies that wait for that day will be too late. So you have to start working on it now to be ready when real quantum computers are available. So if you are a hardware manufacturer like we are, start learning about how the chips are made, how there are different modalities of quantum computing. We are in the superconducting camp along with IBM, Google, Amazon, a few other companies. But there are different modalities: trapped ion, pure atoms, topological approach, spin, and different companies are taking different positions. It's quite possible that many of these modalities may coexist, and for some applications, superconducting may be better. For some other applications, trapped ion or pure atoms may be better. We don't know when we are in. This is like a little bit of a science project going on. So that's what we mean by embrace the fact that we are in an uncertain world, no pun intended. We are in the quantum world here. And we have to keep working away at different aspects of the quantum computing stack to figure out where we will end up. So where do we go from here? As we improve the fidelity and the qubit count, we are going to be able to deal with more and more practical applications. We think at Rigetti that when we are at a couple hundred qubits or maybe 300 qubits at 99.5% fidelity, we will reach what we call narrow quantum advantage, which is when we can start showing that quantum computers are better than conventional computers for many practical applications. We are already working with some of the companies like Standard Chartered and HSBC or Moody's on working on things like economic recession prediction. Right now, Moody's, with all the data that they have, can predict economic recession accurately only 25% of the time. And that's why the joke that economists predict only 19 out of the last 17 recessions correctly. If with quantum computers, even with simulations, with Moody's, we have shown that your statistics improve from 25% accuracy to as much as 75 or 80% accuracy. Not perfect by any means, but a significant jump from 25%. So now we are working on larger databases with companies like Moody's and other organizations. With Standard Chartered, we are looking at fraud detection. Only 0.01% of the world's financial transactions are fraudulent, but they cost us hundreds of billions of dollars a year right now. Can we detect those transactions with quantum computers better than classical computers? Those are the kinds of problems we are trying to solve. We at Rigetti are enabling an interesting experiment right now with many national labs and universities around the world. So we are building this low qubit count, noisy quantum computers. As I said, not useful for any practical application, but very good for research purposes so people can start experimenting with the different parts of the stack, be it hardware or software or user application. So we enabled 9 qubit quantum computers, and we sold the first few ones to DOE's Fermi Lab in Chicago, DoD's Air Force Research Lab in New York, recently to Horizon Computing in Singapore. That's an initiative funded by the government of Singapore. And in the UK, we are working with the National Quantum Computing Center in Harwell, and we are planning on shipping a 24-qubit quantum computer sometime middle of this year. The goal of this projects, and we'll continue to work with other national labs and universities around the world. And really, these are research tools. We want those universities and national labs to experiment with our quantum computers, give us feedback. We fundamentally believe that an open modular architecture of a quantum computer is the way to go. We don't want to close off the system. I know some of our competitors, particularly large big tech companies, view quantum computer just like a mainframe computer, that they have to control the whole stack themselves. We are in the opposite corner. We want outside innovation to come in. We are working with partners like Riverlane in Cambridge and Q-Control in Australia, and we are allowing them to innovate using our fundamental technology. We think that's the right way to enable a quantum ecosystem, and that will foster innovation at a faster rate. That's what we mean by embracing quantum society. So let's give the world the tools, the research vehicles, and let's see what we all come up with. One of the questions asked here was, what is a bold prediction I can make about quantum computers? As it is, it's an uncertain world in quantum computers. It's hard to come up with bold predictions in any field, for that matter, certainly in quantum computing. But one of the things that the thought has struck me is, if you look at some of the presentations by Professor Michio Kaku from the City University of New York, he has made some very relevant comparisons of a quantum computer to a human brain. And what he has said is, nature has given us a perfect quantum computer, and that's the human brain. Our job really is to try to build something that gets close to it. I find that analogy quite relevant. Many things that we do in the lab right now are actually reminiscent of what may be going on in a human brain. We have millions of neurons that are entangled. We deal with analog inputs, and a few neurons act on it, and out comes the output. We don't quite understand what goes on when those neurons are interacting. But it's all analog world, and we do get the correct output most of the times anyway. And that's really how quantum computers are working. We are doing with statistical projections the likely outcome, and that's how we get the answer. So as it happens, my daughter is doing PhD in neurosciences right now. And I look at some of the stuff that they do, and she's at NIH in Washington, DC. And they are doing some sophisticated experiments with neuroscience-related work. And when I look at what they are doing and what we are doing, I definitely think that some of the breakthroughs we may get in quantum computing may come actually from fields as far as neurosciences, and vice versa. That is, some of the stuff that we are understanding at a fundamental physical level may actually help neurosciences in the long term. So my bold prediction is somewhere in the next 5 to 10 years, we may connect these fields, neurosciences and quantum computing, because the similarities are very eerie in nature. And as I said, Michio Kaku has already said, nature has given us a perfect quantum computer, and that's a human brain. So let's see how close we can get to that. That's all I have for the time being. I'll come back for Q&A. Thank you for your attention.